Yes, and obviously Anton needs no introduction. And the title is Immersions with Small Normal Curvature after Gromov, which is extremely interesting to me.
After Gromov.
After Gromov, yes.
Okay, so I will share some couple of observations which I learned from couple of two latest preprints of Gromov, and I will try to make it. I mean, yeah, the idea is to make it an entertainment, right? Talk. So, but let me start from. So the main question. Assume I have a manifold, and I want to immerse or embed, doesn't matter, into small manifold. Small manifold manifold of large dimension, and I want to make it so that normal curvatures are small.
May I ask a quick question? Because it's something we just recently, like this week, discussed with Misha Gromov in particular. When you said embed or immerse doesn't matter, right?
Yeah, absolutely doesn't matter. The dimension, the target space has huge dimension, so it's right.
Oh, it has
generic.
It's just not natural dimension. Yeah, then yes. Okay, thank you.
I don't care about the like optimal bounds for dimension. So like I don't know, like so if dimension dimension of M is n, let us assume that I don't know, target space has dimension 100, 200 n. Yeah, that will be enough, right, for all practical purposes. Yeah, so we want to, the point is that we want to have control on normal curvature, curvatures of embedding. So, and maybe you can check your intuition if you didn't know the question. You can like what possibilities will be. Do you think any manifold admits an embedding into unit ball of large dimension with normal curvature, with fixed normal curvature bounds, or this bound goes to infinity as dimension n goes to infinity? You don't have to answer me right now, but I mean, try to answer for yourself, and you will see. Or if it's bounded, like what should be bound, right? Roughly, yeah. Maybe let me state.
Sorry, are you asking for uniform bound? Regardless of
is it true that any closed smooth manifold admits an embedding into unit ball with uniform bound on normal curvature? What do you think? You are usually have courage to answer.
For curve, just for curve, you ask the curvature to be less than 1.
Yeah, right. For curve, what about any manifold? Any closed manifold?
So the curves.
What's right? What's your statement? Do you think there are manifolds with arbitrary large that require arbitrary large curvature, or it stays bounded?
That I don't know.
Not right. Okay, so it is actually stays bounded, and in fact, just a second, yeah. In fact, the bound is, sorry. In fact, the bound is square root of 3, roughly, right? And I suspect that bound is optimal, right? And I will talk about this. So that's roughly.
So could you repeat the question? What is the question?
So I have arbitrary closed manifold, and I want to consider immersions or embeddings, doesn't matter, in the unit ball in Euclidean space of large dimension. What like can I embed it with, like, so the statement is that any closed manifold admits an embedding into unit ball with normal curvature less than square root of 3. Okay. So, but let me maybe, before I do this, let me talk a little bit about history of the question. Okay. So I think it was Ferry, and it's I think 1950, who solved the problem for curves, right? And there is a nice theorem, right? If you have a closed, like if gamma is closed curve, closed, smooth curve in the unit ball, arbitrary dimension, then average of curvature is greater or equal 1. Okay, like on gamma. So I will quickly, like I will indicate the proof without actually proving this, right? So we have, that's my unit ball, and I have some closed curve there. First of all, obviously this bound is optimal, right? If you travel around the unit circle, the curvature will be 1 all the time. Okay, so to prove this, you just consider the distance function from the origin squared over 2, right? And reduce this function, you reduce to the curve. And after that, you take it like express its second derivative in terms of normal curvature, integrate it, and you get that, you get the statement. Sorry, Yuri, you should turn microphone off. Yuri Dmitrich, please turn microphone off. Okay, so so that's the result of Ferry. And by the way, Sergei Tabachnikov has a survey on this theorem. He collected maybe a dozen of different proofs, and yeah, and it seems like you cannot do much better at first. Well, but you can do something, right? So you can pretty much repeat the proof of this statement and prove the following. If, what happens with oh no, it's okay. So if M is closed submanifold in unit ball, say dimension of M is equal to n, then absolute value of mean curvature, average, okay, then average of absolute value of mean curvature is greater or equal than n. Okay, so the proof is exactly the same, right? You just take the square root of distance function to the origin, and you rewrite Laplacian of this function on the manifold in terms of mean curvature and integrate, right? So the integral of Laplacian is 0, right? So that gives you eventually this bound. So this is stronger than, somewhat stronger than direct corollary of Ferry's result. So for Ferry result, you can you can apply Ferri result for any manifold, right? You apply Ferri result for any geodesic, you get that average curvature of any geodesic is at least 1. And by Liouville theorem, you get that average normal curvature of any submanifold, closed submanifold in unit ball is at least 1. But this statement is stronger, right? So you the average of mean curvature is at least n, that is stronger than average normal curvature bigger than 1, right? So like the normal curvatures might look in different directions, and average might be formally smaller, right? So yeah, right. So now let me and again, right? So it seems like you cannot get better, right? If you just take sphere, then it is like its mean curvature exactly n, right? So and it lives in the ball, right? So but now what about arbitrary manifold? And there is a like first observation by Gromov, it's compression lemma. Maybe I'll change the color. Compression lemma. Roughly, it says that to do any manifold. Roughly, let me write. It's sufficient to consider a torus, right? Tn is sufficient. To prove everything. I will say what exactly I mean, prove everything, by everything. Yeah. So what I'm trying to say, that assume I can find an embedding of torus with small normal curvatures. Okay, then I can find embedding of any closed manifold with small normal curvatures. Why? Because I can take my manifold, embed it into Euclidean space. So assume this is dimension n over 2, right? And this is n. So by Whitney theorem, I can embed it smoothly. And I rescale it so that curvature, normal curvatures, nearly 0. And then I map the Rn to torus, and then to unit ball using the, like, assuming that I know the n embedding with small normal curvatures. And of course, the normal curvatures in the torus will be almost 0. And the only part which will matter is the normal curvature of torus itself. So if I can embed torus of twice larger dimension with small normal curvatures, then I can embed the manifold. Questions? I think that's kind of principle. It's simple observation, but it's principle for everything that follow. Yeah. Okay, so next thing, we need to find an embedding of torus. And there is, what's happening? This is okay. And there is a obvious choice. There is a Clifford torus. Clifford in the sphere of dimension 2n minus 1. So it's in particular, it's in the ball of dimension 2n, which is like product torus, right? So what's and of course it's a bad one. right? This is not a good embedding. So what's happening with principal curvatures of the Clifford torus? It's normal curvatures, I mean, not principal. So the normal curvatures lives somewhere in between 1 and square root of n, right? If I draw the torus like this, right? That's factors of S1. If I go in the coordinate direction, the curvature will be square root of n. If I will go in diagonal direction, the curvature will be 1. And you can actually write a formula for curvature. So if you take in Euclidean space, you take unit vector. Okay, then to find the curvature, you have to measure this norm of this unit vector, unit in the L2 norm. You measure this vector in L4 norm. So why I wrote L4 large, not small, because I want certain normalization. I want vector well, right. So it's proportional, right? Like actually, you let me just write it like this. Let me make it L4, and then you multiply it by square root of n. If I didn't make mistake, yeah, I think I didn't. Yeah, I think that's correct formula. So that's the curvature, normal curvature in the direction, right? So it's just simple calculations there. So again, if you take diagonal vector proportional to like 1, 1, 1, right? Then curvature will be 1. If you take coordinate vector proportional to 1, 0, 0, 0, the curvature will be square root of n, and that will be 1. Okay. So now you want the idea is to find subtorus, like nice flat subtorus of the Clifford torus, such that its curvatures will be bounded. And well, it seems like a reasonable choice to find a direction where all normal curvatures are the same. Okay, what's this direction? It's a subspace in Rn, in Rn, such that L4 norm over L2 norm is constant. Okay, and of course we know that by Dvoretsky theorem that if dimension is large, then this ratio will be almost 1 for most of directions. Okay, but in L4, it's a polynomial thing, it's algebraic thing, simple, so you can actually find exact match, right? There are plenty of if dimension n is large enough, then you can find arbitrary given dimensional subspace with such constant ratio of L4 over L2. So let me state it again, right? So you cut L4 by certain subspace, and in this cut you get Euclidean metric from L4. Okay, and then you need to calculate, and I will not calculate in the like in real time, but I will tell you the formula of what you can do is you can make constant curvature square root of 3n over n plus 2. Okay, so it's smaller than square root of 3. Okay, and in particular, you get that any manifold, so like from this, you get any closed smooth manifold M admits an embedding M to ball Q, right? It was ball. Okay, Q is large enough with normal curvatures smaller than square root of 3. So there is little gap here between this value and that value, right? And so this little gap can be used to find first an embedding into Euclidean space with normal curvature small enough, and then apply the example of this, say, let's call it diagonal of Clifford embedding, diagonal Clifford embedding, to get needed square root of 3. And of course, you can make little bit better bounds for given some dimension, but if dimension is large enough, it's approach square root of 3. So let me maybe say little bit. I'm not sure if I spent roughly half of the time, right? Let me at least say a couple of words about this embedding, right? So this embedding which I described is on the level of fundamental form, a second fundamental form is completely symmetric, right? So you take any rotation of tangent plane, tangent space, and you can find rotation of normal space, so that your second fundamental form become the same as before, right? So you have like the rotations of tangent plane, group of rotations of tangent plane extend to automorphisms of this second fundamental form. So again, let me state it again, like the second fundamental form takes two tangent vectors and returns normal vector. Okay, and there is OT, right? The orthogonal group of T that acts on tangent vector, and there is an action of this orthogonal group on N that preserves this second fundamental form. So there is one obvious choice for such second fundamental form. It's unit sphere, right? That has this property. So in this case, the action is trivial. But there is another choice. It's Veronese embedding, like sphere Sn maps to, I forget, sphere n plus 1 over 2 minus 1, I believe, right? So this is Veronese embedding, and it's also has certain second fundamental form, more complicated, but it's still symmetric one. And the and of course you can combine them together. You can take linear combinations of these two second, like you can add normal direction, and you can combine these two second fundamental forms to get all the second fundamental forms with complete symmetries. And it's easy to check that this is the this is complete, like the completely symmetric second fundamental forms, just two-dimensional, right? They form two-dimensional space. If you somebody interested in algebra of this thing, I will tell, but just I want to have one person who is interested in this, right? So if somebody wants to know a little bit more about this, tell me. Nobody? Okay. Okay, so
Oh,
now
maybe tell us something about it.
Okay. Okay. So so there is a what I usually denote by phi. There is a external curvature tensor, right? So that's also, as usual, tensor takes let me call it V. VW, right? It takes 4 vectors, and that E can be expressed using a second fundamental form, a very straightforward way, right? You take scalar product of, it was V, right? Of second fundamental forms for these 4 vectors. Okay, this vector, this curvature tensor, it's nice because it's as usual, curvature tensor takes only tangent vectors, doesn't need normal vectors, right? And it remembers everything about usual curvature tensor. You take symmetrization and you get Riemannian curvature tensor. Okay, but it also has certain things. If you take complete symmetrization, so that's lives in lambda2 of t. But you also can get another symmetrization to get to S4 of t. That's completely, that's essentially homogeneous 4-degree polynomials on tangent space. Okay, and if you want it to be completely symmetric, you want both things, this projection and this projection, to be symmetric. Okay, so there is a theorem about curvature tensors. The curvature tensors, if it's completely symmetric, it must be proportional to curvature tensor of unit sphere. So it's just one parameter here. And another parameter here is like it's roughly average of square of normal curvature. Okay, and these 2 parameters describe it completely, right? And I think it's like a little miracle that torus admits such a symmetric, like such embedding, right? It's not symmetric with respect to rotations because it's torus, right? But its second fundamental form as symmetric as second fundamental form of Veronese embedding, which is completely symmetric thing, right? So like, I don't know, yeah. So I think I answered question, but if there are, if you, maybe I made your life more complicated by answering this, by the way. So if you want to ask more, please do. Otherwise, I will go to lower bounds on the normal curvature. No questions about this? Okay. Okay, so now the question, what about, so we have this bound on the curvature, square root of 3 times n plus 2. That's for embedding of manifold into unit ball of large dimension. You can, by the way, the embedding was actually into sphere, right? We could ask the same question about embedding into sphere, and then straightforward calculations show that what we get is the n minus 1 over n plus 2, right? So that's the optimal, like that's the bounds we get for this diagonal Clifford embedding. Okay, so that's a normal curvature in the sphere. Is this if you add 1, then you get from here to here, right? If you take square, add 1, you get from here to here. Okay, so now question: are these bounds optimal? And let me say what I know, right? So that's this one is optimal, and I suspect that this one is optimal. Probably yes, but this one is optimal. Optimal in case if dimension is 2 and dimension is 4, right? So there are certain certain problems, right? So like if you ask for asymptotics when n goes to infinity, then what I can do is 8/3, right? Like instead of 3, square root of 3, I get square root of 8/3, right? Which is a little bit less than needed, and kind of surprising that there is a problem here. So that's what I'm going to spend the remaining part of talk is about optimal bounds. Okay. So and yeah, and I'm kind of proud, like it was kind of my contribution to this, that one of the formula that Gromov wrote in his preprint was correct, but actually you could make it square root of 2 better, right? And that was this way I was able to get optimal bound for the sphere, right? And I will tell you where the problem is for the embedding into ball, right? So what's so essentially it's Gauss formula. You have to write Gauss formula for scalar curvature, right? And here it is. Scalar curvature is equal to 3/2 h squared minus n plus 2/2 times k squared. So this is mean curvature vector, and this is I write k squared because I want to make clear that it's positive, right? But actually k squared is average of normal curvature squared, right? So this is I mean quite straightforward, right? Once you want to relate these 3 quantities, it's quite straightforward to check that this is true. So essentially you check this formula for hypersurface and observe that every quantity in this formula is linear with respect to adding dimension, right? So if your normal space has dimension, say q, then you add this formula q times and you get the same thing, right? So that's kind of not nothing surprising here, right? And now what the scalar curvature? This is formula for the Euclidean space. If you want it to be for arbitrary manifold, you have to add, like you have to subtract scalar curvature of submanifold minus scalar curvature twiddle. That's roughly scalar curvature. That's you add the sectional curvatures of ambient manifold, like in all tangent directions to the submanifold, right? So if if ambient manifold is a sphere, then scalar curvature twiddle is n times n minus 1. So it remembers only dimension of the submanifold, right? And now you want to check that the torus embedding, which the diagonal Clifford embedding, which I described, has optimal bound on curvature. You just apply this formula. What you get here, like the torus must have non-positive scalar curvature at some point. Therefore, this part is at least like is less than n times n minus 1 at some point. Okay, so this thing might be 0, you don't know, and that gives you some lower bound on normal curvatures. That's finished the proof. Okay, so now what about embedding into unit ball? Right. First of all, notice that if the embedding, like we know that average mean curvature is at least n, right? So if the embedding was flat, as like the induced metric on the torus is flat, then you get the same thing, right? This difference is 0, and average of this thing is at least n square, right? And then you just get an equality for average normal curvature, and this is optimal one, right? But if you consider non-flat tori, then situation is worse. What you can use that for any Riemannian metric on torus, scalar curvature is less than 0 at some point. So this is yeah, you can use this statement, and in particular, if you have some metric on the torus, then every conformal change of it, if you change it with conformal factor, then again you will have some point with non-positive scalar curvature, and this implies the following thing, right? So that for any positive function u, you get this, that this thing, which I just wrote, takes non-positive value at some point. Okay, for any positive smooth function u from torus to reals. Okay, so and you can use this inequality, like you use this fact on the instead of negativeness of scalar curvature, and it turns out that in dimension 4, like this coefficient is especially nice. It just match and gives you exact bound, and for others it doesn't match, right? So like it gives you little less than you want, and I'm sure that it's true, right? But just like, yeah, so that's the place I want to stop. Any questions?
Well, first of all, let's thank the speaker. Very interesting. Thank you. Yes, as Anton said, time for questions and such, discussions, whatever.
I just want to ask a naive question. When we will refer to those n are these bound of curvatures proved results or still guess?
Which results?
The lower bound. So the lower bound when you
so there, let me state where what's known, what's not known, right? So for maps, for embeddings into sphere, yes.
This is not
exact bound, no, exact bounds. Flat embeddings of torus into sphere. Oh, sorry, or into ball. Okay, again, yes. So, but it's flat, right? With flat metric. If not flat, then we get yes in dimension 2, which I didn't discuss, but it's pretty much Gauss-Bonnet formula. It's easy. And dimension 4, right? And for the rest, we get little less. As I said, instead of square root of 3, asymptotically, we get square root of 8/3. So it's 1/3, like square gets by 1/3 less than needed. So that's this part is open. Okay, but in principle, even if there is a better bound, I don't believe there is a better embeddings. I quite sure that this is optimal. The bounds I discussed were optimal, but even if there is one, it will not improve main result, right? So like in order to apply the compression lemma, you need flat torus, right? It's just like question of yeah, can you make it or not, right? Like just this. I think it's a funny question, kind of fundamental and yeah, and simple at the same time, right? So did I answer? That was your question, right? Yeah.
Yeah. So what would happen if n is when n becomes large?
So you need Q to be large also.
Q to be
right?
large, yes. First Q to be large.
Right. So
what would happen?
So when you fix n, you make much bigger Q. Then everything works. If not, then it's different story, right? So the bounds are. I mean, there is some control. Just maybe read Gromov. He write a little bit about lower dimensions of Q. Right, if it is the question. So like, maybe I didn't understand your question. Like if dimension is large, if n is large,
yes,
if n is nearly infinity, then bound getting to square root of 3, it's known.
Okay.
Right, and lower bound is 8/3. Right, that's what we know for large dimensions, right?
Okay.
So that was the question, right? Yeah.
Yes. Yeah. Okay. Yeah. Thank you. Yeah.
You're very welcome.
Do you have a rough idea how large Q is needed?
No, like square. You
square.
need, right? Like maybe 2n squared, or I don't know, 5n squared, something like this. But square would be enough. Should be enough.
So it's about the next dimension.
Yeah. Maybe a little larger, but I mean, you need a special. Yeah, but look, what you need to make this like just the question about L4 ball, right? You take L4 ball and you need a section, Euclidean section inside. That's the bound, right? Like you need a n-dimensional section in n-dimensional L4, right?
So it's quantity of Dvoretsky.
Yeah. Kind of Dvoretsky, right? You need exactly Euclidean, right? But it's algebraic question, like a question how many polynomials of type x, like linear function to the power 4, you need to express Euclidean metric squared, right? I mean, let me write G, right? You have Riemannian metric G. You take a square. It's a homogeneous polynomial of degree 4 on the tangent space. And now you can express it using linear functions in the power 4, of course. Question: how many terms you need in this representation? So you can explicitly find like using the convexity tricks, right? The question: you have a point inside of convex cone, right? How many extremal points you need to take it as a linear combination with non-negative bounds? Okay. So we finished.
Yeah, I think so. So let's thank the speaker again. Honestly, I have quite a few questions, but I probably will send them by email to some people who I know are interested in this stuff. So thank you very much, Anton. Then I'm closing the meeting, right?
Okay. Okay.
Okay.
Thank you.